Okay, so we'll just jump right in there, see if we get through part one. So here's this, we've been talking about all matter is made up of atoms. I love the atoms. And we'll look more closely what an atom is made up of its parts later. But for now, we're trying to work on this logic tree. Matter can either be a pure substance or a mixture, and we talked on Friday a lot about elements. Elements is one of two types of pure substances. We have a periodic table in here, and we'll be talking more about the different elements and how they differ. But I want to talk more about compounds now. So a compound is a pure substance, and you know the repeating unit. So we use chemical formulas, like the chemical formula for water is H2O, exactly. So we know that if somebody says, I have a cup of water, that means that they have H2O molecules running around. That is their repeating unit, okay? As it turns out, water is one type of compound. Actually, it's a molecular compound. And I kind of want to talk just briefly about the two types of compounds. But water is an example, and I have a figure here to show you that water actually can be broken down into, if it's H2O, it can be broken down into H's, hydrogen, and O's, oxygen. So you can break it down. The ordinary means just means no nuclear chemistry. So we're not doing nuclear chemistry this semester. So notice that on Friday we talked about 7 diatomic elements. What are the 7 diatomic elements? Here's my fingers. Hoffernickel. Exactly. So it's hydrogen, oxygen, fluorine, bromine, nickel, or nitrogen, and chlorine. What did I miss? Fluorine. I think I missed Hoffernickel. I missed the F in Hoffernickel. Okay, so there's 7 diatomic elements. Now, as those atoms want to buddy up with another atom, just because of how their kind of electrons are around that atom, they want to be a diatomic molecule, but they aren't a compound. That was going to be my point. Like an H2 molecule is not a compound because it needs to have atoms of 2 different elements. So it's kind of a small thing, but it's kind of interesting. So you guys told me the formula for water is H2O. The formula for carbon dioxide is CO2. Of course, remember we said carbon monoxide. What's the formula for carbon monoxide? CO. It is CO, exactly. So remember, that's the example where we said, what's the symbol for the element cobalt? C little o, exactly. Exactly. That was my point. So kind of keep on that. Okay, ethane, 2 carbons, 6 hydrogens, calcium sulfate, 1 calcium, 1 sulfur, and 4 oxygens. So notice that we use subscripts, and I don't know if I mentioned this the other day, but one of my pet peeves is you guys would tell me this is the formula for water. This is not the formula for water. I don't know why people do that, but you'll see it. Like we make it a little superscript. That's okay. So compounds, we use chemical formulas to represent the compound. That's the repeating unit. It's either going to be, there's 2 types of compounds coming up, but you can break the compound into its pieces. Like I said, water, you can break it into hydrogen and oxygen, okay, by ordinary chemical means. And I have an example here. We'll see if this plays for us. I'm having kind of video issues, so instead of the video I would usually play, here is actually one from the internet. You know, how does this go? You know that a chemical reaction has happened if new substances are formed. How do we know new substances are formed here?
Mercury was left in the bottom of it.
Yeah.
And there was nothing like the powder had. So.
The powder went away and it was replaced by something totally different. Yeah. And it generated a gas. So, yep. Cool. So compounds can be broken down by ordinary means. In this case, the ordinary means was just applying heat. In this example, the ordinary means is applying electricity. So when George Bush, the second one, was in office, I know he talked about going to the moon, and I am so for that. I just, I'm for exploring space. Why not go to the moon, make a colony, right? So I mentioned that because I think he mentioned this. Of course, hydrogen is a great fuel if you're careful with it. H2 gas, okay, it can be a fuel. So this actually, if you use electricity, you run it through water, it breaks your water down into hydrogen gas and oxygen. Okay, how would you describe the levels? The one on the, left to right, the one on the left is oxygen, the one on the right is hydrogen. How would you describe those volumes that are being captured up there?
2-to-1 ratio.
It's a 2-to-1 ratio, and that's pretty awesome. That's exactly because water is 1 oxygen of atom and 2 oxygens of hydrogen. That is so cool. But anyway, George Bush, he might be onto something. Who knows? So he can't really pronounce nuclear, but I'm just kidding, sort of.
Did you spell it wrong?
I think he pronounced it wrong, and I probably pronounced it wrong, but I'm not president.
I don't think it was his idea. It's probably the smarter people.
Yes, he probably got fed that. But I think that the source of all good politicians is to surround themselves by scientists that know what the heck they're talking about. So, very good. So those are 2 examples of breaking a compound down into getting its elements, right? So just briefly, and we'll be talking more about this, after we have to talk about atoms, and then we're going to talk about atoms joined together to make compounds. So actually, those are kind of 2 different units in here. But there are 2 different types of compounds. There are molecular compounds, and actually, I might have mentioned it. Water, H2O, is an example of a molecular compound. And then there are ionic compounds. What's the formula for table salts?
NaCl.
It is 1 Na and 1 Cl, exactly. And what do we call it? What's the chemical name of it?
Sodium.
Sodium chloride, yes. Yep. Anyway, sodium chloride is an example of an ionic compound. Okay, and I'm going to kind of give you just a brief look at a little bit of the differences between molecular compounds like water and ionic compounds like salt, table salt. So first off, molecular compounds, we call them molecules. So molecular compounds are always molecules. So we know that we have a molecule, a water molecule, okay? But if you have something that's an ionic compound like salt, actually the repeating unit is called a formula unit. So we wouldn't say I've isolated an NaCl of, we wouldn't say a molecule of sodium chloride, we'd say a formula unit of sodium chloride. So that's one difference. Okay. Let's see. These are all examples, like the caption says, of molecular compounds. You see water up here. Now I know there's some extra blue dots, and we'll be talking about what those little extra blue dots are, but hopefully you recognize the oxygen and the 2 hydrogens. One of the things about molecular compounds is you can take your hand and go all the way around them in all directions. They are their own little entity. Okay, then we have methane and ammonia are also examples of molecular compounds. This actually is just emphasizing the idea that you can put your hand around them. They are a little family unit. They are an island amongst themselves, kind of. So this is a figure from your textbook showing you that ever important resource, water, gushing out. And remember, we can't really look at water, each individual water molecules per se. We can look at what they do collectively. And it's hard to kind of get a picture of them. So ionic compounds like sodium chloride, table salt, you would use the term formula unit if you were going to get one little piece of that, okay? Now the thing that's different, I have a video, so I'll turn around here in a minute. The thing that's different is that you can't take your hand and put it all the way around and say, I've got my formula unit, because they're all stuck to each other. This is a good example of being all stuck to each other. Mercury 2 oxide's an ionic compound, just like sodium chloride. And so it's kind of like I could circle this as a formula unit. I could circle this as a formula unit. I could circle this as a formula unit. This, they're all stuck together in what we call a crystalline lattice structure. It's like a, yeah, it's very organized, very awesome. I think all things considered, I'm gonna, oh, yeah, we'll look at the first part of this video. How are we doing? See it? Ish.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale.
That's where I think
Many
I'll pause.
chemical reactions occur through a series of steps.
But I think that is notable that, like, sodium metal, very nasty stuff. In fact, I think I might have mentioned yesterday, or not yesterday, when we were in the lab on Thursday, I think I might have mentioned that our chemical storeroom has recently been visited and basically gutted of all of our fun stuff. I know it was not really fun. But we had sodium in there, and it's relatively, could be dangerous. We had a bunch of sodium in there. I didn't buy it. The guy probably 50 years ago bought it. So anyway, sodium reacts violently with water. Some of you may have seen videos where they take sodium and throw it in water, or maybe your high school teacher did that. So sodium's nasty. Chlorine gas is nasty. But if you combine the two chemically, you get something you put on your food. I just think that is so cool. Think about it. And we're going to talk about properties coming up this week. But okay, now that what you saw on the video or whatever, that very exothermic, giving up a lot of energy, that was an ordinary, not unordinary. That was ordinary chemistry. Okay, so basically no nuclear chemistry going on there. So in other words, you can take elements, put them together by ordinary chemistry, chemical reactions, and get compounds. Okay, so this is, I think, a figure from your textbook kind of showing you the alternating green, purple, green, purple, green, purple, and they would represent the sodium chloride, sodium chloride, sodium chloride. Okay, and as it turns out, when ionic compounds form, and we'll talk more about metals and such, but sodium is a metal, aluminum's a metal, iron's a metal, magnesium's a metal. Sodium's also a metal, and sodiums tend to give up electrons and they get smaller. So I know just by looking at this that the purple is the sodium and the chlorine is the big one. So just to kind of one last slide introducing you to the idea of compounds come in two flavors: molecular compounds like water and ionic compounds like sodium chloride. Okay. So here is an assignment, and I will take a picture of this and send it out email so everybody, in case you don't have your textbook. Okay, so this will be due on Wednesday. I lost track of what today was. So
Are these problems out of the textbook?
What's that?
Are these problems out of our book?
They're out of your book, yep.
Okay.
And like I said, if you're kind of still working on getting your book, I'll send a screenshot. What a terrible drawing of a test tube and oh my goodness. Oh. It works.
Time constraints.
Yes. Talent constraints or time constraints.
I've seen worse.
That's nice of you. Okay, so let's go on and see if we can kind of wrap up this part. We'll see. So yes, this is that same figure. Okay, this is a figure that should be burned in your brains. So matter is made up of atoms. Matter has mass and occupies space. And matter can either be a pure substance or mixture. And we've talked about pure substances, elements and compounds. Now we need to talk about mixtures. So I think I told you the other day, what word did I say for a homogeneous mixture? Or what is, not what I said, but what is a homogeneous mixture? One that's the same throughout, exactly. What about a heterogeneous mixture? I said it's chunky, it separates, exactly. Very good. You got it. Okay. Okay, so there are two types of pure substances. There's an element. A substance, if it's pure, can either be an element or it can be a compound, like we were just talking. I must take lots of words out for this one. You know, I do record lectures, so they are kind of pushed out there, both available from the Twitter feed and from the course homepage. So I know in some of my other classes, sometimes students go back to if I talk too fast. But if I talk too fast, you can slow me down. But if I talk too fast. So I kind of feel like we've kind of hit this concept pretty well. Early on in this course, sometimes students will say, now when's it going to start to get hard? And my goal is it won't. It'll just be, go for that A. Okay? So mixtures are different than compounds because with a mixture you have just basically taken substances, two or more pure substances, and physically combined them, just toss them. Now sometimes mixtures are more obvious than others. I had somebody the other day ask me about metal alloys. I don't know if you're kind of familiar. I'm not real familiar. But like stainless steel is a combination of different, and you get different grades of stainless steel with different amounts of zinc and
Carbon.
okay, zinc and carbon, and does it have magnesium in it too? I don't know.
I couldn't tell you that much. I know that carbon's used in steels a lot for hardness.
Okay. So my point is that when you get stainless steel, basically it's a mixture. It's suspended mixture of atoms that are not chemically bonded together. They're just hanging out. They're frozen together. Okay, so they don't have chemical bonds. They have what we call intermolecular bonds, like we talked the other day. Okay. So a mixture is two or more substances that are just physically combined. And the cool thing about mixtures is you can separate, usually, there should always be a way to separate your mixture back out into its components, and then they will just go on about their lives as their own, they keep their identity. So, yeah, you guys are probably okay with this homogeneous mixture and heterogeneous mixture. When we homogenize milk, we mix the milk really good so it doesn't separate into its layers. Heterogeneous mixtures are, I use the word chunky, that basically if you look at the chunk of matter as a whole, you can kind of see the little different components popping out. A good example of a heterogeneous mixture would be like a pizza, maybe? It's a mixture. How could you make a pizza homogeneous? Put it in a blender, yeah. If somebody had jaw surgery and really wants that pizza. Well, no, maybe not. So if we were to be able to kind of look at the very detail and the atomic level of stuff that's going on, say you mixed up your pizza in a blender, right? Oh my gosh. You should be able to look closely and still find molecules of pepperoni, molecules of bread, molecules of tomato. Okay, so to me that's a good example of can you really separate it back out into pepperoni and tomato? I think it'd be hard. We do a lot of distillation in chemistry, where basically maybe the boiling point temperature of pepperoni is different than the boiling point temperature of tomato. Let's just
Wouldn't
say,
be edible.
yeah, let's just say tomato boils at a lower temperature. You could get your tomato and you could grab that fraction, keep boiling till more temperature and get your pepperoni. It's kind of disgusting, but yep. So these are some examples kind of from left to right, and you guys probably, what do you think? So let's start with the left one. How many people think this is a homogeneous mixture? Me too. How do we know, if I say, how do you know it's a mixture? Caption says it, but what were you gonna say? Well, if I said the base is water, how would you know it's a mixture? Because it's not, yeah, there's something in it to potassium chromate to make it yellow. Don't drink yellow water, yes. How about the other one? How many think it's a homogeneous mixture? How many think it's a heterogeneous mixture? Heterogeneous, what makes it heterogeneous?
So you can see the separations.
Yes, you can see the separations. You can like have three things here. We know that there's something solid in there, gel maybe like, and we know that there's water, but water is clear and we see the purple. So I'm thinking at least three things. Yep. Yep, yep. Very good. Okay, left to right. How many people think the first one's homogeneous? Me too. I think the second one's heterogeneous. Me too. How do you think we could, if we had the patients, separate that thing there on the right back into its components?
By color.
By color. What if, weight, I like that, maybe density, maybe something will float. What if the black stuff is, looks maybe carbonish, but what if it was iron?
A magnet.
Like magnet, yep, and the other stuff magnetic, very good. Or size that you can separate in all mixtures out. How about the first one? How can we separate it out into, let's just say it's, well, it looks like some sort of blue, probably salt compound that's dissolved in water. How can we drive off the water and be left with the compound?
Heat, oil.
Heat, boil? Very good. Yep, you got it. So this is kind of neat. Again, it's hard to, figures are nice in science because we really can't see the molecules like you see it over there, okay? In this room, actually, we have about 80-20 mixture of nitrogen and oxygen, and now hopefully those are part of the Hoffer-Nickel series. So actually you can see why nitrogen is 2 little balls and oxygen is also a pair of balls. And then down here, let's see if we can count. We got water, okay? And if you take salt, salt's a great thing at dissolving in water. So here we have that would be our sodium is our plus, and the minus is the chlorine. Okay, so that's a mixture. So mixtures can either be homogeneous or heterogeneous. And we've been talking a lot about a solution, like a potassium dichromate solution here, or a solution of blue solution, that sort of thing. If your solution is if your mixture is homogeneous, then we can call it a solution. Okay. So stainless steel, guess what? Homogeneous mixture, stainless steel is an example of a solution. It just has to be a solid solution. I think that's kind of cool. So solutions generally contain, there's a lot of S's in liquid chemistry. Okay, so we have the solution, which is the mixture, and it contains a solvent and a solute. One way to, I think, remember that is if you were going to go revarnish your furniture, what would be one of the first steps you do? Sand it. But after you sand it, or when you sand it, do you take some sort of clean it off. Yeah, some sort of liquid. Sometimes you would go and get like a varnish remover. Okay, varnish remover oftentimes is called just a solvent. Okay, so there you go. A solvent is the thing in larger amount that basically kind of, in that case, takes off the lesser amount of material. Okay. So we've had some slides that talked about aqueous solutions. So aqueous solutions means that the thing doing the work there in large amount, that solvent, is water. Okay. Is this the last slide? Dun, dun, dun. So these will also be due on Wednesday. And I put underneath there what you're going to be doing. So for instance, and also, did I mention this before? That Tro, like he should, actually has the answers to the odd ones on the back of the book. So answers to 33, and by the way, 33 is very similar to 34, and the answer to 35, very similar to 36, are in the back of the book. And so the first set, you're supposed to say what sort of mixture it is, and for the second set, you're supposed to say, is it pure or is it a mixture? Remember, substance, a synonym for substance is pure substance. So is it a pure substance or is it a mixture? And then the problem goes on to say, if it is a mixture, say whether it's homogeneous or heterogeneous. Okay. So I hope that works for you. And unlike I teach, unlike some of my other classes, you don't have to use complete sentences, okay? In case you're wondering. Any questions about that? Okay, and I'll email this to everybody. And that's all I have for today. Out early again, oh yeah.